Okay, I'm going to talk about chromatic dispersion. We're going to do this in the shortest possible time. We will cover the definition of chromatic dispersion. We'll take a look at rainbows and prisms, which are real life examples of chromatic dispersion. We'll take a look at chromatic dispersion in fiber and how it affects some other components in modern telecommunication. All right, the definition. The speed of light depends on its wavelength, or if we can substitute in the word color for wavelength. Chromatic dispersion is abbreviated as CD. The index of refraction is a measure of how much light is slowed down when it's entering a media, like a piece of glass or water. Typically, the index of refraction decreases as the wavelength increases. So if we order the colors, and the index of refraction of red is less than the index of refraction of purple. The larger the index of refraction, the more light will bend from its original direction. Notice here that the colors are split. That's because the different colors have different indexes of refraction. Notice here on a prism how the colors are bent to different angles and that the purple is bent much more than the red. On a piece of fiber, we have a nice start with a nice short pulse with multiple colors, multiple frequencies, multiple wavelengths, however you'd like to say it. And those wavelengths spread out by going through the fiber because there's different indexes of refraction. The red is slowed, but the purple is slowed more than the red. The unfortunate part is the wider the pulse, it's going to reduce the bit rate that can be put down the piece of fiber. All right. So what we're going to do is we're going to use a principle called zero chromatic dispersion. Chromatic dispersion materials can be crafted that have negative chromatic dispersion. So you take a piece of cable that has negative chromatic dispersion, pair it with a piece that has positive, and you have a net zero chromatic dispersion. What I'd like you to notice in this piece of fiber that has negative chromatic dispersion, how the order of the colors are changed. How now red is going to be slowed more than purple. Unlike here, where the purple naturally is slowed more, we can engineer things so that the red is slowed more. Again, putting the two of these together will give us a net zero chromatic dispersion. All right, the negative chromatic dispersion fiber is expensive and it leads to a lot of energy loss. So there are other ways that we can achieve zero chromatic dispersion. We can use a Bragg grating. We can use pairs of prisms. We can use a chirped mirror. We're going to take a look at chromatic dispersion in two pieces of telecommunication equipment, the wavelength selective couplers and lasers. All right, the wavelength selective coupler coming into the coupler here is going to be multiple colors of light. They're each going to hit a filter, and the filters are tuned to the different colors of light. So we're able to separate the colors of light out to their individual components. This is called demuxing. We can use this in reverse and take the different colors and putting them in the same beam, which we call muxing or multiplexing. This device can also be used to filter selective wavelengths, like we only want the blue color. All right, lasers. The index of refraction, as the index of refraction increases, so does the energy drain. And what will happen is a nice square pulse where this to the right is increasing wavelength right from left to right. And we have the pulse entering the fiber, and here we have the pulse exiting the fiber. The higher wavelength has a greater index of refraction, which means it's going to lose more energy. So what we need to do is tailor our pulse before it goes into the piece of fiber so that there's more energy at the higher wavelengths. So the end pulse at the end is what we want. All right, so we talked about how the speed of light in a media in glass, fiber, water is dependent on its wavelength. And we said that wavelength could be the synonym for wavelength is color. This leads to chromatic dispersion. We can correct for chromatic dispersion, and that chromatic dispersion is also the limiting factor on the speed or our run lengths of our cables.